Okay, so chapter 15, I think we will solve one problem related to chapter 15, and then we will shift to chapter number 17, which is compressible flow. Okay, so we will talk about compressible flow while we are studying compressible flow in the thermodynamic course, although it is fluid mechanics related domain where you have studied compressible flow and incompressible flows. Okay, so starting towards the Okay, so this problem I think you have already solved in the previous lecture. Okay, so I'm not going to solve this where we have already solved for the enthalpy of combustion. Okay, so coming towards the next question. Okay, so first you have to read the statement. Calculate the lower and higher heating value per kg of mixture at 25 degree Celsius. Okay, for the stoichiometric mixture, air and benzene, given that the enthalpy of combustion at 25 degrees Celsius are uh, mentioned over there minus 3169500 kilojoule per mole for C6H6. Okay, so you have to note it down the data and then we will see that how to solve it. Okay, so starting from the chemical equation. Okay, so the chemical equation I will always try to provide with the problem statement. Okay, so you do not need to remember it at how to build the. So we have benzene C6H6 and it is mentioned in the gaseous form, plus we have 7.5 O2 in the gaseous form, 7.5 79 by 21. Okay, so for example, this chemical equation is provided with the problem statement. Okay, so here, if you can notice that we have benzene and air, and then there will be some, due to the chemical reaction, there is some product which is CO2, H2O, and N. Also, the phases are also mentioned with each of the element, or you can say CO2 is in the gas, H2O is in the gas form, N2 is in the gas form. Okay, if you can remember from the previous lecture, we already said that if in the product side the H2 is in the gaseous form, so it's mean the value of enthalpy of combustion is called low heating value. Although it is, if it is in the vapor form, so it is called high heating value. Okay, so this comes from the previous lecture. We already see in the previous lecture. Okay, so here it is clearly mentioned that H2O is in the product is in the gaseous form. Okay, and if you can go towards the problem statement, the enthalpy of combustion of benzene is also known to you, which is C6H6. I can say enthalpy of combustion in kilojoule per mole, which is equal to minus 3169500 kilojoule per mole. Okay, so it's mean the first required thing which is asked in the question to find is the low heating value. Okay, so you can directly say that your low heating value is basically absolute value of enthalpy of combustion. Okay, and this is 3169500 kilojoule per mole. Okay, similar thing if I can ask that if it is mentioned here it is vapor form, so you can directly find the high heating value by using the available data. Okay, so this is the first thing which is required in the problem statement. Okay, so now here it is asked also to find the lower heating value per kg of mixture. Okay, so as I already told you that every time whenever we have to calculate lower heating value, so most of the time it is in kilojoule per kg. Okay, here we have to find the lower heating value of mixture. Okay, so what we have to do, just you have to divide 3169500 with the number of moles of mixture and molar mass of mixture. So what is the mixture? Mixture is basically combination of benzene and air. Okay, so you have to divide, you have to calculate the number of mole of every thing, and then you have to multiply with the molar mass. Okay, so I am going to directly write over there. Okay, so you have to calculate by yourself. Okay, so you have to calculate the number of mole of mixture and molar mass of total mixture. Okay, for example, this come towards 78 plus 240 plus 790. Okay, so you can just divide it and you will get 2861 kilojoule per kg. So this is required that we have to find lower heating value of the mixture. Okay, so that's why we have divided number of mole of mixture and molar mass of mixture. If it is say that you have to find lower heating value of only benzene, okay, so only the fuel, so then you have to divide number of mole of fuel only and molar mass of fuel only. Okay, so this is the thing. Okay, next thing which is required is to find the higher heating value as well. Okay, so if you can remember from the previous slide that your higher heating value is equal to lower heating value plus mass of H2 in the product side into latent heat of vaporization HFG. Okay, so this is this equation we already see in the previous lecture. Okay, so lower heating value we have with us. Okay, so here we can find first in kilojoule per kilomole, and then we convert into kilojoule per kg of the mixture. So lower heating value come from this point 3169500. Mass of water vapor you have to multiply 3 into molar mass, which is H2O. So 3 into 18, it is I think 54. And HFT you can look towards the thermodynamic table. Okay, it's the same table which we look in the steam power plant section. Okay, so HFG at 25 degrees C, so its value is 2442 kilojoule per kg at 25 degrees Celsius. Okay, so now you just have to plug all the values. So 3169500, mass is 3 into molar mass of H2 H18, and HFG value is 2442, which come from thermodynamic table. Okay, for the water. Okay, so if you can solve it, you will get the higher heating value. Okay, so you have to note it down, and I will just move towards the next slide. Okay, so for example, our high heating value is equal to, if I can solve it, it will be 3301368 kilojoule per mole. Okay, so now the required thing is to find heating value for the mixture, high heating value for the mixture. Okay, so simply you have to divide this term with the number of mole of mixture and molar mass of mixture. Okay, so you can easily convert in kilojoule per kg for the mixture. Okay, so for example, this will be equal to 3301368 and 78 plus 240 plus 790. Okay, so this you have to verify by yourself that either this is true or not. 78 plus 240 plus 790, and this will be equal to 2980 kilojoule per kg for the higher heating value of the mixture. Okay, so this is the solution for this type of problem. Okay, so if you have any question, you can ask me, and then we will move towards the next topic. Okay, so at this point we will stop reading chapter number 15. Okay, the rest of the question you can easily find in the end of the book. Okay, so you can just check the question which related to the topic and practice it by yourself. Okay, so if we have some time at the end of the semester, so surely we can practice more questions related to chapter 15. Okay, so now coming towards the new chapter, which is compressible flow, and chapter number 17. Okay, so here you can already see there's some figure related to fluid mechanics, which is aeroplanes are moving. And okay, so here the main important point is why we are going to study the compressible flow in the thermodynamic course. Okay, so the reason is that when we are talking about high speed flow, okay, and for example, I will assign some problem to you that you have to find that you have to perform thermodynamic analysis of the wing of aeroplane. Okay, although previously we studied that over most of the cases we assume that the fluid is incompressible because the velocity is very low. Okay, for example, in the pipes or somewhere, okay, like this. But however, when we are talking about the high speed flow, the density is not constant. Okay, because if we assume that density is constant, so it will completely wrong assumption. Okay, so that's why we have to look for the compressible flow, because if density is not constant, then what is the effect if there will be increase in temperature? What is the effect if we can just decrease the temperature? And how to perform thermodynamic analysis for the compressible flow when we assume that density is changing? Although in our real life there is no fluid which we call as an incompressible flow. This is always an assumption that we consider that the fluids are incompressible flow, and this assumption is based on that in order to simplify our problems. Okay, although in our daily fluids, water or in blood in our veins, all are compressible flows. Okay, so coming towards the main definition of compressible flow. Okay, so the compressible flow is that flow in which the density of the fluid changes during flow. So all real fluids are compressible to some extent, and therefore their density will change with change in pressure and temperature. However, if the relative change in density is small, the fluid can be treated as incompressible. Okay, so this is the only condition. If we just assume that the relative change in density is very small, so then we can consider that the fluid is incompressible. So compressible fluid such as air can be considered as incompressible with constant density if change in elevation are small, acceleration is small, and temperature changes are negligible. Okay, so this is the condition for which we can say that our fluid is compressible, that is air. However, air is also incompressible. However, air is also compressible fluid because density changes. So the gases are treated as compressible fluid, and study of this type of flow is often referred to as a gas dynamics. Okay, so where we have to where we have to see this compressibility effect in our problems related to the thermodynamics. So the some important problems where compressibility effect has to be considered are flow of gases through nozzles and orifice, compressors. Okay, so you already know that in the steam power plants or in the power generation process, compressor is one of the important part. Flight of aeroplanes, projectile moving at higher altitude, water hammer. Okay, and this last thing we will discuss in the next topic that. Okay, so this is also related to the sounds. Okay, so compressibility effect, the drag coefficient of body by formation of shock waves. Okay, so this we already also study in the coming slide. What are the shock waves and how these shock waves are formed when compressibility is there in the fluids. Discharge coefficient of measuring devices such as orifice meter and pitot tube, stagnation pressure, and flow in converging and diverging section. Okay, so that's why we are going to study the compressible flow. Okay, because most of our thermodynamic processes involve nozzles. Okay, and then we have to look for the analysis of these thermodynamic problems by assuming or by considering that our flow is compressible flow. Okay, so now there is one condition by which we can figure it out that either the flow is compressible or incompressible. Okay, and that is by using the Mach number. Okay, so I hope you already familiar with this term. What is Mach number? Mach number is basically the measure of importance of density change for compressible fluid, and it is the ratio of local velocity of fluid divided by velocity of sound, and we denote it with as a sometime ma or nma. Okay, so this is the Mach number, and just a rule of thumb that our Mach number is less than 0.3, so the case is considered as a incompressible fluid, incompressible. However, if the Mach number is greater than 0.3, it is compressible flow. Okay, so if you can see in this question velocity of fluid, for example, if I will just look towards the problem related to the aeroplane thermodynamic. So where this velocity of fluid come from? So basically this velocity of this is the local velocity, and this is the local velocity. For example, I say that the aeroplane is moving with 370 meter per second. So this is my local velocity, and at the elevation, for example, our aeroplane is moving or flying at some height of 18,000 meter, and the temperature for at that height is something you can say 23 degrees Celsius, or you can minus 23 degrees Celsius. So I have to calculate velocity of sound at that temperature. Okay, so then I can calculate the Mach number. Okay, and similar thing, if for example, if I can say there is uh, one particle which is moving in the pipeline. Okay, so and that particle is moving with some velocity. Okay, for example, you can say it is in the piston cylinder arrangement of your car. Okay, so from that point the local velocity is known to me, and then I have to calculate the velocity of sound inside that combustion chamber or inside that piston cylinder arrangement. Okay, so this is the basic thing from where we can judge that our Mach number is less than 0.3 or greater than 0.3, so that we can easily solve our problem related to the compressible flows. Okay, so Mach number I already explained to you. Okay, so which is the ratio of local velocity v and speed of sound. So speed of sound is denoted by c. Okay, and if Mach number is less than 0.3, incompressible flow, density changes are negligible. So if your Mach number is in between 0.3 and 0.9, so we call as a subsonic flow, and it is a type of compressible flow. Okay, because our Mach number is now greater than 0.3. Okay, so our density effects are important in this case, but shock wave do not develop. Okay, so this shock wave we will discuss that how the shock waves develop. Then if your Mach number is 0.9, in between 0.9 and 1.1, so it is called transonic flow, and shock waves appear and divide the flow field into subsonic and supersonic region. So similarly, if we have Mach number in between 1.1 and 5.0, so it is called supersonic flow, and shock waves are present and there are no subsonic region in it. And if our Mach number is greater than 5.0, so it is called hypersonic flow, and very strong shock waves and property changes you can see in this type of flow where the Mach number is greater than 5.0. Okay, so these all are the types of compressible flow. Okay, so subsonic, transonic, supersonic, and hypersonic. Okay, so before starting towards the real problem related to the compressible flow, so we just quickly go through the some equations which we already know. So ideal gas equation you already know, P is equal to rho RT. Okay, so it is just a review from the previous. Okay, and then if you can notice that specific volume is equal to 1 over rho, okay, which is 1 over density, and PV is equal to RT. Okay, so then for an ideal gas, the internal energy is a function of temperature only, and ideal gas specific heat at constant volume is defined as Cv du by dt. Okay, so this relation you already studied in the previous classes, that your change in energy and internal energy is equal to Cv delta T. So the same equation comes from. The Cv is basically function of temperature, but for moderate temperature changes it can be taken as constant. Change in internal energy between two states is considered constant, considering constant Cv. So delta U is equal to Cv delta T. Okay, so these are the equation. which we most commonly use in the coming slides as well and coming problems as well. So then you already know enthalpy is basically U plus RT, or you can say P over rho. And for the ideal gas, enthalpy is also a function of temperature only. Ideal gas specific heat at constant pressure is defined as Cp dH over dt. And if you can say there is another relation, delta H is equal to Cp delta T. And this is, I think, one relation which we didn't use previously. Cp minus Cv is equal to R. Okay, R is basically the gas constant. Okay, and Cp is the specific heat at constant pressure, and Cv is specific heat at constant volume. Okay, so the proof of this we will look. I think we will just quickly do the proof so that you can not confuse that how this equation come from. So again, this is K, specific heat ratio, is equal to the ratio Cp over Cv. And if we can combine above equation, so which equation we are going to combine? So this equation and this equation. So we will get Cp is equal to R K divided by K minus 1, and Cv is equal to R divided by K minus 1. Okay, so these are the equations we commonly frequently use in compressible flows. Okay, so then some other equation which is delta S. Okay, so change in entropy. So you already know from the chapter number 7. Okay, that how you can relate for change in entropy with temperature and densities. Okay, so these are some equation, and I will just quickly do the proof. If you do not know that how this come from Cp minus Cv is equal to R. Okay, so basically this come from the simple equation which is H is equal to enthalpy is equal to internal energy plus PV, and you already know PV is equal to mRT. And if you can just differentiate both of the sides, so it will be dH is equal to du plus mR dt. Okay, so and now if you can already know that dH is basically mCp dt and du is mCv dt plus mR dt. Okay, so from here you can easily cancel dt terms, okay, from both of the side, and also you can cancel mass. Okay, so from here we get the Cp is equal to Cv plus R, or you can say Cp minus Cv is equal to R. Okay, and now if you can put the value of K is equal to Cp over Cv in this equation. For example, I put the value of Cp in this equation. So what this equation become? So this equation become K into Cv minus Cv is equal to R. Okay, and from here I can say that if I can take common Cv, so Cv is equal to R divided by K minus 1. Okay, similarly if you put the value of Cv over there, which is Cp over K, so you will get another equation which is Cp is equal to Kr divided by K minus 1. Okay, so these equations are important because you have to use these equations in the compressible flows. Okay, now the another equation which is the speed of sound, C under root KRT. K is in this case which is the specific heat ratio of the working fluid, R is the gas constant, and T is the temperature. Okay, so the proof of this equation first we will look into that how we have to develop this equation. Okay, because this is the important proof. Okay, so we will solve first. Okay, so in order to prove that C is equal to under root K R T. Okay, so first thing you have to consider one piston cylinder arrangement. Okay, so for example, I just consider that I have one piston, similar arrangement over there. Okay, and our piston is at this time at somewhere here. Okay, so this is our piston. And inside there is some fluid with some specific heat. Okay, so here, for example, we can say that. Okay, so first thing, you already noticed that I have to explain that what is sound. Basically, sound is basically a wave. Okay, and it is called as a pressure wave. Okay, and we define sound as a weak wave. For example, if I am talking right now. So these are some waves which are producing some signals, and then you can hear my voice. Okay, and these waves are called pressure waves and weak waves because it cannot burst your eardrums. Okay, so that's why we call as a weak wave, which is a sound wave. If the same wave, for example, if I am talking and your ear drum burst, okay, so it's mean that these are the shock waves. Okay, so these shock waves are another form of the waves, and we will discuss this. So right now we are talking about sound waves, which is the weak wave. Okay, so for example, because we have to look into the compressibility effect. So this is the first arrangement, which is piston cylinder arrangement. So our piston is, for example, at this point A, at the initial stage. So after I will just give some velocity to this piston. For example, I just supply small change in velocity, so which is dV, for example. Okay, so this piston move towards some point, so some small distance. Okay, so for example, I just say that the small distance is at D. Okay, so now this is my piston after supplying some velocity. Okay, and when I supply some velocity, so it's definitely move some distance. Okay, and that distance, we, for example, we can say that the velocity which we are supplying is dV is equal to dx over dt. Okay, and if we can say that it moves towards the small distance, so it's mean that dx become dv dt. Okay, so this is the thing. Okay, so I can say that this distance is dv dt. Okay, a small distance. Okay, and same thing I can just say that some sound is okay, some waves are moving, okay, because I'm moving the piston, so definitely there was some development of some waves inside your piston cylinder arrangement, and we called as a sound wave. Okay, and we denote with that it is moving towards the, that wave is moving with the velocity c inside your piston cylinder arrangement. Okay, and in order to define the velocity of this wave, okay, so we can simply say that c is equal to, okay, and one important thing is that our total distance of the piston is L. Okay, and from here we can say that this C is equal to L by dt. Okay, so we can say that this is the velocity. Okay, and then if we can notice that after our cylinder move towards the point number B, okay, so we can say that this distance become L minus dV dt. Okay, so this is a very easy thing because I will just minus L with this term. Okay, so then I will get the remaining distance, which is when your piston is at point number B. Okay, so these are some common terms before we can start with the proof. Okay, and then yeah, you also assume that the area of your piston is A. Okay, from here. Okay, and then okay, so first thing, in order to prove this C is equal to KRT, so you have to apply the mass conservation. Okay, so here we are talking about x direction. Okay, so you have to apply mass conservation on the x direction. Okay, so mass conservation in the x direction. Okay, so mass conservation you already know, mass in is equal to mass out. Okay, so this is the basic term which you can already study in the fluid mechanics as well, that how you can say that mass conservation has need to be applied. Okay, and this is the steady flow condition. Okay, so now here if we can, okay, another important thing is, for example, I can just take a control volume of that specific wave which we are talking about. That wave is formed when our piston is moved towards point number B. So definitely there will be a compression now. Okay, so after compression, what happened to our control volume? Okay, so for example, I say that this is my wave which is generated when my piston moved towards point number B, and I can just say that this is my control volume. Okay, so in order to analyze only this section, okay, so this is just a wave. Okay, you can say it is a sound wave. Okay, and a pressure wave. Okay, so for example, before compression, okay, so the velocity is c, okay, and density is rho. So this is the before compression when my piston is at point number A. After compression, when the piston moves towards point number B, so velocity becomes c minus dv. Okay, so this we will look when we are going to prove that how this velocity becomes c minus dv, and also you can have some basic understanding from your mechanics courses that if after after compressing, so this is where we are talking about the relative velocity, so that's why c minus dv. Okay, so do not confuse this term, we will look into it when we are going to prove it. Okay, now after compression, the pressure become P plus dP, okay, because there is a increase in pressure, and then the density, because here we are talking about the compressible flow. Okay, so density is change. Okay, so after compression, it become rho plus d rho. Okay, so this is my, for example, I can say this is my initial stage, and this is the final stage after compression. Okay, so by using this data, we can say that our mass is basically, so you already know mass is equal to rho into volume. Okay, so from here I can say rho into length of my cylinder, piston cylinder arrangement, into area of the cylinder. Okay, this is my initial point. So then mass out. So similar thing. So after okay, sorry, this is not out. So this is mass final. Okay, so final, which is we are talking about the point after compression. Okay, so after compression, the density become rho plus d rho. Okay, so after compression, length become L minus dv dt. Okay, so we already see from the figure dv dt, and then area is same. Okay, because area cannot be changed over there. Okay, so from using the data which is C is equal to L by dt. Okay, so from here I can simply put the value of L, which is L is equal to C dt. You can say in this equation. Okay, so this equation which we already developed. So right now I'm going to put the value which is rho into C dt into area. Okay, similar thing I have to put the value of L over there as well. Okay, so rho plus d rho C dt minus dv dt into area. Okay, so this is the equation. Now from here I can easily eliminate area. Okay, because area is the same thing. Okay, and then if I can further solve it, it turns out to be Okay, and dt also can be eliminated, because if I can take common dt over there and dt from this equation, because this is multiply, so dt can be eliminated, okay, easily. So my equation become rho c is equal to rho c. Okay, so I am going to multiply rho plus dp with c minus dv. Okay, so before this I can write one another equation so that you will get some understanding. So rho c is equal to rho plus dp, d rho, change in density, c minus dv. Okay, so if you can notice that the final velocity becomes c minus dv now. Okay, so the same velocity I have wrote over there, that after compression the velocity becomes c minus dv. Okay, so now if I can further solve it, it turns out to be rho c is equal to rho c minus rho into dv minus c into d rho, or minus dv d rho. Okay, so this is our equation. Okay, and here we can assume that this dv by d rho is very small. Okay, so this is one assumption, or you can say, because if dv is small, d rho is also small. Okay, and if two small things multiply together, so it comes another small figure. Okay, so that's why we can just say that this is a very small thing, so that's why we can eliminate, and we can assume that it is approximately equal to 0. Okay, so from here rho c can be eliminated. Okay, so now our final equation become rho dv is equal to c d rho. Okay, so this is one equation which we can use in order to further analysis. So you can denote with the equation number 1. Okay, so till now you can just note it down, and then we will move towards the next step. If you have any question, you can also ask me. Okay, so now these are the figures from your books. Okay, so you can just correlate it with this figure. So this is the same figure which I already draw in the previous slide. So now in the second step, in order to prove that c is equal to under root k rt, you have to apply momentum conservation. Okay, so momentum conservation. Okay, so momentum conservation you already know from your fluid mechanics as well, that F net is equal to mass flow into final velocity minus initial velocity. Okay, so F is equal to m dot into delta V. So this is the mass conservation. Okay, so for example, again I am considering my control volume over there. Okay, so this is the control volume which I already talked in the previous slide, that at the initial stage its parameters are h, p and rho. Okay, so here we are also saying that enthalpy. So, and after compression we get the increase in all the values, which is P increase to delta P, rho increase with delta rho d rho. Okay, so and our velocity becomes C minus dV after compression. Okay, so this is initial and this is the final point. Okay, so now if you can remember from your mechanics that, for example, if I want to apply some pressure, if for example due to the velocity there is some pressure that is developed inside this piston cylinder arrangement and for specific control volume. Okay, so the pressure you can put the pressure like this. So this is my pressure and that is putting on the control volume. Okay, and also the pressure. Okay, so inside if there is a flow and there is some pressure involving and some specific point, so P is, so there will be pressure from the both side. Okay, so P is acting towards the left side as well and P is acting from the right side as well to the control volume. Okay, so from here I can easily find the F net. Okay, so F net basically pressure into area. Okay, so you already know force is equal to pressure into area, and then the force after compression become P plus dP into area. Okay, so this is how you can calculate the F net on the control volume. So m dot is basically rho area into velocity. So rho AV. So here we are talking about the sound velocity because we are simply figuring it out that we are talking about the wave that is related to the sound. Okay, so that's why we write the C. Okay, rather than V. Okay, so final velocity C minus dV after compression. So C minus dV, and the initial velocity is C. Okay, so now you can just simplify this equation, and if you can simplify you can see that area will be eliminated from here. Okay, C can also be eliminated. Okay, and if you can further solve, the equation turns out to be minus okay, and this P can also be eliminated because PA minus PA. So dP is equal to minus rho C dV. Okay, so this is another equation and you can simplify it further. So rho dV is equal to dP by C. Okay, so this you can denote with the equation number 2. And you already remember that we have already built equation number 1 in the previous slide. Okay, so what you have to do is, so you have to simply put the value of from this. So you can say that put the value from 2 to equation number 1. Okay, so equation number 1, if you can remember, rho du dV sorry is equal to C d rho. Okay, so rho dV you have to simply put in this equation, which is equation number 1. Okay, so now this equation become dP by C is equal to C d rho. Okay, so now this is my equation for the further analysis, and which is dP by d rho is equal to C square, and from here we can say C is equal to under root dP by d rho, and you can say it is for isentropic condition because we are assuming that this cylinder is insulated and there is no heat and this is an adiabatic process, Q is equal to 0 over there, and so that's why we call it as a isentropic and it is a reversible. Okay, so this equation you have to note it down that this is equation number 3. Okay, so this equation we will use for the further analysis. So till now you have to note it down and then we move towards the next part. If you have any question you can also ask me. Okay, so now here we can simply find the value of dp by d rho. Okay, so you already know that P into specific volume and the power of specific heat ratio is equal to constant. Okay, while we are talking about the isotropic process. Okay, so here we already know from the previous that specific volume is 1 over density. Okay, so from here we can simply say P over rho K is equal to constant. Okay, so now what I have to do is I have to apply the differentiation on the both sides for this equation. You can say equation number 4. Okay, and after differentiation, so differentiation you have to apply by yourself because it's the mathematical knowledge. Okay, so you can figure it out that what is the differentiation. So I am writing down the final term. So dp by d rho is equal to k p by rho. Okay, this is the final term after differentiation of equation number 4. Okay, so this you can figure it out by yourself. Okay, so here I can simply write that pv is equal to rho rt. Sorry, p is equal to rho rt. Okay, and I can put this value in the equation. dp by d rho is equal to k into rho rt by rho. Okay, so from here this is basically rho. So rho can be eliminated. So dp by d rho is equal to k r t. Okay, and from here if I can put this equation number, you can say 5 into equation number 3. So what will be the final thing? So c is equal to under root k r t. Sound for the isentropic flow and for the adiabatic condition is k r t under root. Okay, so if you have any question you can ask me. So this is an important tool, so you have to understand it because this is where we have to start the analyzing compressible flows.